All right, future chemists, let's talk about something that I promise you will be on your SPM paper, Voltaic cells. Now, I know, it can seem kind of tricky, but trust me, we're going to break it down so simply that you'll actually be excited to see these questions on your exam. Ready? Let's get into it.
Okay, before we really dive deep, here's your secret weapon. Think of this as our private tutoring session, right? And what does every top student need? Practice. So after this, I want you to go test yourself. Scan this QR code right here, or just head over to MCQ SPM.com. You can drill past your questions on this exact topic. Seriously, it's the best way to make sure all this stuff really sticks.
Right, let's get down to it. The electron tug of war, how voltaic cells really work. So, how in the world do you get electricity from just, sticking two pieces of metal in some liquid? It seems like magic, doesn't it? But nope, it's pure chemistry. And the best way, the absolute best way to get it is to think of it like a game of tug of war, but instead of a rope, we're pulling electrons.
So what is a voltaic cell, really? Well, you can think of it as this super clever little gadget. It takes the chemical energy that's naturally stored inside different metals and just flips it into electrical energy. And the whole thing happens because of a spontaneous redox reaction. Whoa, big words, right? Don't worry. All that means is that electrons are naturally jumping from one thing to another. That's it.
Okay, imagine the game. We've got two different metals, or two competing teams. One of these metals is, let's just say, more generous with its electrons. It's more electropositive. Think of it as the stronger, beefier team that just shoves the rope, the electrons, away. When it loses those electrons, we call that oxidation. Now, where do those electrons go? They've got no choice but to travel through the wire connecting them, and boom, that flow of electrons is your electric current. And on the other side, you've got the weaker team, the less electropositive metal. It's just sitting there ready to grab those electrons as they come flying over. Gaining those electrons, that's what we call reduction. And there you have it. That simple push and pull is what powers the whole thing.
Okay, pay close attention here. This is where so many students get tripped up on the exam. We can't just call them stronger and weaker metals forever. They have official names, the anode and the cathode. So let's get this straight. The metal that loses electrons, our stronger one, is the negative terminal. We call it the anode. And here's your memory trick. AN-ox. Anode is oxidation. Got it? So that means the other metal, the one that gains electrons, has to be the positive terminal. And we call that the cathode. The trick for this one, red cat, reduction at the cathode. Seriously, burn AN-ox and red cat into your brain. If you can remember this, you've just dodged one of the biggest mistakes students make.
Okay, part 2, decoding the exam questions. This is a tutor's guide. So the theory is cool and all, but what really matters is how you use it to score marks, right? Let's get practical. We're going to switch hats now and think like the person who writes the exam paper. I'm going to show you exactly how to break down these questions step by step.
Check this out. This is a real past year question. It says, which statement is true? Electrons flow from zinc plate to copper plate through the external circuit. This is a super classic setup, zinc and copper. The question isn't designed to be tricky, it's a direct test. Do you really understand the electron tug of war? So how do we solve this? Easy. We follow a simple process every single time. Step 1. What are our two metals? Zinc and copper. Got it. Step 2. Which one is more electropositive? You just have to know your electrochemical series. Zinc is higher up than copper, which means it gives up its electrons way easier. Step 3. Apply the rule. The more electropositive metal, zinc in this case, is our anode. And what happens at the anode? Oxidation. It loses electrons. So step 4, the final conclusion, where do the electrons flow? They have to flow from zinc to copper. See? Simple logic.
All right, here's another classic exam trap they love to throw at you. They'll ask something like, what increases the voltage? They want to see if you know how to make the battery more powerful. And you don't need to memorize a million different metal pairs. You just need to know one simple principle.
And here it is, the big secret. To get a higher voltage, you just need a bigger difference in electropositivity between your two metals. Think about it this way. The further apart the two metals are in the electrochemical series, the more mismatched they are in our tug of war. That means you get a way stronger push from one side and a way stronger pull from the other. A stronger tug of war means a higher voltage. That's literally all there is to it.
Let's put this into practice with a real example from a past paper. Say you've got a cell made of lead and copper. The question is, how do you get a higher voltage reading? Well, we know the rule. We need to make the gap between the metals in the electrochemical series bigger. So what's the solution? Replace lead with magnesium. But why? because magnesium is so much more electropositive than lead. It's way further away from copper on that list. This creates a massive push of electrons towards the copper, giving you a much bigger voltage. Easy.
Section 3, Mastering Voltage Calculations. We have a formula for success. Okay, we've got the concept down, we've got the logic for the multiple choice questions. Now for the final boss, the calculation. Don't sweat it. The exam might ask you to calculate the exact voltage, but honestly, it's just one simple formula.
And here it is, the magic formula you need to know. E naught cell equals E naught cathode minus E naught anode. Okay, what does that mean in plain English? It just means you take the electropotential value of the cathode and subtract the value of the anode. A really simple way to remember it is you're always taking the more positive number and subtracting the more negative number. Just like this in your head. Cathode minus anode. Say it with me. Cathode minus anode.
All right, let's solve a real one. The question gives us a magnesium/copper cell and their E naught values. Step 1, identify the potentials. We've got negative 2.38 volt for magnesium and positive 0.34 volt for copper. Step 2, which is which? Well, copper has the more positive value, right? So it's our cathode. Magnesium is the more negative one, so it's our anode. Step 3, plug it all into the formula. E naught cell equals the cathode's value, which is positive 0.34, minus the anode's value, which is negative 2.38. And stop right there. This is the trap. A minus and a negative together, what does that make? A plus. Subtracting a negative means you're actually adding. Don't fall for that one.
So when we do the math, 0.34 plus 2.38, we get our final answer, positive 2.72 volts. And that's it. See how it all comes together? Once you know the rule, the formula is actually pretty easy.
Okay, next up, your 7-day study plan, from zero to hero. I know we just went through a ton of info, but you can absolutely master this. To make sure you do, I've laid out a super simple step-by-step plan. Follow this for just 1 week, and you'll go from being unsure to feeling like a total pro on this topic.
Here's the plan. Days 1 and 2, we're just hitting the core concepts. All you need to do is master that tug-of-war idea and be able to define anode, cathode, oxidation, and reduction without even thinking. Days 3 and 4, it's practice time. Jump on the MCQ SPM app and just hammer out those questions about electron flow and what affects voltage. Days 5 and 6, it's math day. Your goal is to solve at least 10 calculation problems using our formula. And finally, on day 7, you put it all together. Find a past paper and do the entire REDOX Chemistry section. If you stick to this, you're going to be more than ready. You'll be confident.
So, think about what you just learned. You now get the basic principle behind literally every battery, from a simple science fair lemon battery all the way up to the one in your phone. You know how they work. But that leads to a pretty interesting question, doesn't it? We know these reactions happen on their own, but what if you forced it? What happens when you take a battery and you force the electricity to flow backward? Well, that's a whole other story and the topic for our next session. Catch you then.